In this video, we are going to talk about the envelope in Aspen HYSYS, but before we need to know some terms from this envelope. This is the phase envelope curve. Okay, at the beginning, this is a simple information, like if we have a temperature and also we have a pressure. If we increase the temperature and we have a liquid, the liquid will face evaporation till it turns to be a vapor. Okay, so temperature increasing, we are moving from liquid to vapor. Temperature decreasing, this is the opposite, so we will be moving from vapor to liquid and from liquid to solid. Okay, so if the pressure increase, we have a vapor, this vapor will be compressed and turns to be a liquid. Okay, so the higher the pressure, we are moving from vapor to liquid, and also if we are lowering the pressure, the liquid will be turning into vapor. Okay, so the temperature and the pressure are causing the opposite effect. Like if we look here, if the temperature increases, liquid to vapor. If the pressure increases, vapor to liquid. So you need just to memorize one of them or just understand it. If you are having a liquid and you are increasing the temperature, it will be moving from a liquid phase to a vapor phase. So if we look at this phase envelope, and here we have a temperature. So if the temperature here is increasing, moving in this direction, we are moving from a solid to a liquid, and from a liquid to a vapor or the gaseous phase. Okay, so here by increasing the temperature, so the temperature is increasing, we are moving from a solid to a liquid and from a liquid to a vapor. What is this written? Where is this written? Here, solid to liquid to vapor. Okay, and the opposite, if we are lowering the temperature from vapor to liquid and then to the solid. If we look at the y-axis here for the pressure, if we are increasing the pressure over here, we are moving from a gas, we are moving up, so from a gas to liquid to a solid. So the pressure increasing, we are moving from a vapor to a liquid to a solid. Okay, this is important because here, if we are defining what is this point, this is a triple point. The triple point, the point where we have solid, liquid and vapor. So inside this point or at this condition, we will have the three phases available. Okay, after that we have this important point. Okay, we are here for this point, which is the critical point. The critical point in the x-axis has a critical temperature, and at the y-axis it has a critical pressure. So you will have a T critical and also a B critical. Okay, so let's move on and have a clean one to talk about this one. Okay, so by definition here we have a temperature critical that we need to talk about and define. So what is the critical temperature? By definition, the critical temperature here, this is the maximum temperature, so the T maximum or the highest temperature at which the substance can exist as a liquid. So after this point, if we are talking about higher temperature, like moving in this direction, we can't have a liquid. So even if we are increasing the pressure, so increasing the pressure at this temperature will not lead to having a liquid phase. Okay, so again, the critical temperature is the highest temperature at which our substance can exist as a liquid regardless of the pressure. So at this temperature, the substance can't be liquid. So just before this point, we have liquid phase. After this point, we can't have a liquid phase even if we increase the pressure. Okay, so what is the critical pressure? Here we will have also a critical pressure. The critical pressure will be our minimum pressure. The minimum pressure required for liquefying a gas at the critical temperature. So at the critical temperature here, this is the minimum pressure that we can have to liquefy our vapor. Okay, so if the pressure increases, we are moving from vapor to liquid. But if we are talking at the temperature critical, even if we increase the pressure, we can't move from vapor to liquid, because at T critical we can't have liquid, so no liquid at this point. Okay, so this is the simplest way to define the critical temperature. Okay, also we have two other terms like Cricondentherm and the Cricondenbar. I just want to make sure that you understand that we have here the solid phase, the liquid phase, and the gas phase. So remember, when we talk about the vapor fraction, which is amount of vapor from the total. So if I have the total of 100 and I have 90 of this 100 in the vapor phase, so my vapor fraction will be 90 divided by 100, so it will be 0.9, which means I have 0.9 vapor and 0.1 liquid. Okay, so again we want to talk about the Cricondentherm and the Cricondenbar. Okay, so if we look here in this graph, this is similar to the one that we have been talking about. This is a relation between a temperature and a pressure. Here we have our envelope, that's why it's called envelope. It's looked like an envelope. Okay, we have here the critical point, so here in the x-axis we will have a T critical, and at the y-axis here we will have a pressure critical. Here we have the term Cricondentherm, and over here we have this point Cricondenbar. What is Cricondentherm? Apparently this is the maximum of something, like after this point we don't have anything displayed here. So the Cricondentherm, this is the highest temperature at which a mixture of gas and a liquid. So here we have a liquid phase, here we have a liquid and a vapor, so L and V together, and here we will have a vapor or a gas phase. So when we are talking about the vapor fraction of 0.9, it will be available here. If we are talking about 0 vapor fraction, it will be in this section, because here we only have liquid. If we are talking about vapor fraction equal to 1, it will be in this section, because this one is only vapor. So here, because we have a mixture of gas and a liquid, the vapor fraction must be higher than 0, and also it must be less than 1. Okay, so this is the range of vapor fraction. Okay, so before this line here in this section, we can have a mixture of gas and a liquid. After this temperature, we can't have a mixture of gas and liquid, it will be only in the gas phase. So the Cricondentherm, this is the temperature or the highest temperature at which a mixture of gas and a liquid can coexist together at a specific temperature. In the same way, if we look at the top, we have here a Cricondenbar. At the top over here we have a Cricondenbar, and by definition it will be our maximum pressure or the highest pressure at which a mixture of vapor and liquid, so here we have a vapor and a liquid together. After this point we can't have a mixture of vapor and liquid together, so this is the maximum pressure at which a specific mixture of gas and liquid can't exist at a specific temperature. Okay, so here if we go back to our Aspen HYSYS, before we have created our material stream. Okay, so if we go if we enter in the natural gas here and go to attachment analysis, we have already created from here, create an envelope. Okay, and we have already edited before, so need a stream because already we have one created. So to view this one, we choose it and click view. So here this is our envelope for the NG feed. This is the critical values. So we have here, we have talked about the 2-phase and 3-phase. We are dealing with the 2-phase because we don't have water in our material stream. If we have, we will have a 3-phase critical temperature. So this is the critical temperature and this is the critical pressure. This is the maximum, which is the Cricondentherm and the Cricondenbar. We have defined this before. If we look at the performance, it could be displayed as a table or a plot. The plot will always make sense, that's why we always choose the plot. This is the plot similar to the ones that we have been seeing. So the red one is the boiling point curve. Here we at lower temperature we have a liquid. The bubble point here, this is the curve where we are transferring from a liquid to a liquid and a vapor. This is in blue. We have a dew point curve. Let me make this one bigger. The dew point, here we are moving from a liquid phase to a gas phase, or from a gas phase here by lowering temperature to a vapor phase. Okay, so if we are here, if we look here, we have a critical point in yellow. So this is our critical point. For 3 phase, here over here we don't have a 3 phase, so that's why it's not displayed. What else we have here? So okay, we have covered this one. So you can enter your plot for your information. For the hydrate, I'm going in our next video, I'm going to add water to our material stream and try to do a stream analysis for the hydrate formation.